Welcome to our lecture online, and now we're going to look at the law of thermodynamics in a very different way. This is our third look at the second law of thermodynamics, and this involves the concept of entropy. Now, what does entropy mean? Well, there's different ways of defining it, and I put a couple of definitions on here. One of them is a measure of the amount of energy that is unavailable for work. The other one is, it says it's a measure of disorder. So it's a measure of something. And it's a measure usually of how much energy is no longer available in the universe to do work. And so whenever a thermodynamic process occurs, or in some cases we can look at, let's say, a stack of bricks being pushed to the side where they just kind of fall into a kind of a rough pile like that, we can say that in any process like that, the amount of available energy to work decreases. And let's take a closer look at each of these three examples and see how that works. So the first example is that of looking at a heat engine, and we've done that before. We can understand, of course, that the efficiency is how much work we can do relative to how much heat goes in. But in all circumstances, like we learned before, there'll be some loss of heat, some heat that gets expelled in the exhaust of the heat engine. And so once the heat is expelled, that now becomes a quantity of heat that's no longer usable to do energy. Remember, to do energy, you have to have a heat flow from a hot reservoir to a cold reservoir. Once heat ends up in the cold reservoir, you can do work with it relative to the hot reservoir. You'd have to take that heat and bring it back up here. And that, of course, requires work, an input of work to get that done. So on its own, that will never happen. So because doing work with a heat engine requires heat to flow from a hot to cold reservoir, more and more heat ends up in the cold reservoir. Therefore, more and more unavailable energy, or I should say more and more energy unavailable to do work with. So therefore, the entropy, S, we use the letter S for entropy. I don't know why, but there it is. And so the change in entropy is always going to be positive. Again, that's the amount of energy unavailable for work. Another way of looking at it is, we have these bricks nicely stacked up. Someone comes along, kicks them over, or the wind comes along, kicks them over, and they all fall down. Now we're in a less ordered state, and therefore this has lower entropy and this has high entropy. So the change is from low to high, therefore the change is positive. That refers to this one right here. We call this a more ordered state, and we call this a less ordered state. Less ordered means higher entropy. And here another example, let's say we have a block of ice. Heat comes along, starts heating up the ice begins to melt, turns into water. This is a more ordered state. This is a less ordered state, and one way to look at it is here all the water molecules are locked into a crystalline lattice, so they're very well ordered in a cube. And once it becomes water, they just go everywhere, they roll over each other. So this is higher order, lower order. Entropy goes up because we're in a less ordered state. So you can see that in any process that happens on its own, entropy tends to increase. So how do we express the second law of thermodynamics in terms of entropy? It is impossible in a thermodynamic process for entropy to decrease. Now we have to be careful with that statement, because let's say you have a hot object, you have a cold object, and heat is moving from the hot object to the cold object. It turns out that in one case, entropy will go down. In the other case, entropy will go up. But in totality, the amount that in one case it goes up, in the other part it goes down. If you put it together, the totality, the entropy for the two together will always be greater than zero. So therefore, in any heat exchange, the total entropy change will always be positive. And I'll show you some examples later on how we can calculate that. But this is now another good way of looking at the second law of thermodynamics. And now we're ready to go ahead and utilize this principle in a number of examples coming up in the next so many videos.